Okay, good afternoon, everyone. We were discussing this example in the last lecture. Let y double dash plus a1 of x y dash plus a2 of x y equal to 0, where a1 x and a2 x are continuous real valued functions on interval I. These two are the real valued functions, so that if phi solution of, we call that differential equation as L of y, if phi solution of L of y equal to 0, then so are real part of phi and imaginary part of phi. So we want to discuss this. So let L of y is y double dash plus a1x y dash plus y equal to 0, and phi is solution of this. That means L of phi 0. It's also known that these are the continuous real value functions. Means their imaginary part is 0. Imaginary part of a1x is 0. Imaginary part of a2x is also 0, because both are real value. Both are real value functions. Otherwise, this will not hold. So in complex analysis, you might have discussed, if z is complex number, we can write real part of z as z plus z, or 2 times real part z in which the z plus z. So x plus I by x minus I, which is 2 times x. This z is x plus I. And 2 times, what is imaginary part of z? 2i times imaginary part of z means it is z minus z. So this logic we are going to apply. Here we want to show that real part of phi may be complex value function, and imaginary part of phi are solution. If phi is solution, they are also solution of L of y equal to 0, which variable coefficients are real value. So that means your target is L of real part of phi has to be 0, and L of imaginary part of phi has to be 0. We are not going to differentiate, we are using these things. So L of y equal to 0 implies phi double dash plus a1x phi dash plus a2 of x phi. This is going to equal to 0, which is known to you that phi solution. So I'm just taking conjugate of this, conjugate of everything, phi double dash plus a1x phi dash, and the conjugate of 0 is 0. So taking complex conjugate of this. So what you get here, just separate. The conjugate of addition is separate, you can write phi double dash conjugate plus a1x phi dash, the full thing conjugate, plus a2 of x phi conjugate will be equal to 0, because 0 is 0. So its conjugate will be 0. Next, phi bar Since this is real value, what is conjugate of it? The conjugate of this is nothing but one of it. So conjugate of Z1 into Z2 will be conjugate of Z1 conjugate of Z2, in which conjugate of Z1 is A1x. And this is similarly A2x is also real value function. So its conjugate will be A2x fiber. Because A2 of x, there it is given that they are real value function. Real value असेल त्याचा conjugate तो स्वतःच असतो. ते आपण माहित केलेलं आहे. हे काय दर्शवतो? L of phi bar is 0. आपण दाखवलंय if phi is solution, then so is phi bar. Not all the case, huh? Here your coefficients are only real values, otherwise it is not true. You get A1 bar, A2 bar, the coefficient will be different. A1 bar is same as A1 and A2 bar is same as A2, and then A1 bar equal to A1 means A1 is real value, A2 bar equal to A2 means A2 is real value. That is given in the statement. So you have verified L of phi bar is 0. Now you want to show that real part of phi satisfies. So by the formula of real part, you can write phi plus phi bar. It is divided by 2. So L of phi upon 2 plus phi bar upon 2. This is going to be real part. 2 times real part is same. So as this is linear form of method, L of phi upon 2 plus L of phi bar upon 2. So half is you can take out L of phi, then half is taken out L of phi bar. And what is L of phi? It is 0. And L of phi bar already we have shown. So we have shown that the real part phi also satisfies with the operator. That is real part of phi also solution of L of phi equal to 0. But in which case, if the coefficients are real value, otherwise not. Similarly, we also prove that L of imaginary part of phi is also 0. How will you write this imaginary part? Imaginary part can be written as phi minus phi bar divided by 2 times phi. Phi is a constant that can be taken outside completely. L of phi minus phi bar. So 1 upon 2i L of phi minus L of phi bar. So this is going 0, this is going 0 finally. So L of imaginary part of phi is 0 implies imaginary part of phi is also solution. Is also a solution of L of y equal to 0. So hence L of phi and okay, I should write real part of phi and imaginary part of phi are also solutions of linear differential equation with variable coefficient when phi is solution. And keep in mind that the coefficients in L of phi are real value functions. Otherwise, this example will not work. Yes, everyone got this? लक्षात आलं प्रत्येकाच्या? अनम्यूट करून बोला पण मध्ये काय अडचण नाही. Should have taken some other exercise example. Fine. Two linearly independent solution of equation 3x minus 1 square y double dash plus 9x minus 3 minus 9y equal to 0. For x greater than 1 by 3 means your interval is 1 by 3. Two linear independent solutions condition. Now you have to apply your own logic here. I write yellow part first. 3x minus 1 square y double dash plus 9x minus 3 y dash minus 9y is equal to 0. And your interval is by 3 0. 1 by 3 infinity. This 1 upon 3 is not included. So a1x is 3x minus 1 square. X at 1 by 3 becomes 0. And 1 upon 3 is not part of. So here 1 by 3 is not singular point. Non-singular. So these differential equations can be obtained by dividing this expression. Y double dash plus it can be taken common. X minus 1 divided by x minus 1 square. This will be never 0 here. It is 0 at this point, x and this point y dash minus 9 upon x minus 1 square into y. So get equation y double dash plus 3 upon x minus 1 square y dash minus 9 upon x minus 1 square y. पहले एक एग्जांपल लेते हैं अपन तुलना पूरा कीजिए y double dash plus 1 upon x square y dash ये कैंसिल होना है 1 upon x y minus 1 upon x square y equal to 0 या फॉर्म मध्ये आपल्याला कन्वर्ट करायचं we are going to convert this into this form so that x to the power r is solution of this. So for that what you do z equal to 3x minus 1 मध्ये 3x minus 1 ठेवला बरोबर त्या एक्सप्रेशन मध्ये what is dy by dx then z is a function of x and you are going to apply chain rule. So dy by dz. Thinking that z is independent now for into z by dx. So this is going to be as it is and the z with respect to x is 3. So dy by dx is 3 times dy by dz. In this expression y dash we are going to write. Y dash means this is derivative with respect to x. Next, how you can calculate y double dash? Y double dash means dy by dx square. So it is d by dz of dy by dz. So this 3 is going to take in common into dz by dx. Again, what we are doing d by dx of dy by dx. And what is dy by dx? It is 3 dz by dx. So derivative of this into derivative of z with respect to x. Chain rule we are going to apply. 3 d2y by dz square derivative of z with respect to x is again 3. So it is 9 d2y by dz square. So I'm going to substitute all these values in this equation. Which equation? Y double dash plus 3 upon 3x minus 1 y dash minus 9 upon 3x minus 1 square into y. So what is value of this y double dash? Y double dash का आला 9 d2y by dz square. Y double dash करना 3 upon z. Z upon y dash का था y dash is 3 times. Y dash is 3 times dy by dz. Minus 9 upon z square. What is y? Y is, okay, we should keep y as it is. So 3, 3, 9 can be taken common and divide 9 to both sides. So d2 y by dz square plus 1 upon z dy by dz minus 1 upon z square y equal to 0. So yesterday you have solved this equation by taking solution y equal to x to the power r. Instead of x, you take z to the power r. So what is dy by dz? R z to the power r minus 1. And d2y by dz square, taking r into r minus 1, z to the power r minus 1. Just substitute that value here. So you get r, r minus 1, z to the power r minus 2 plus 1 upon z divided by dz r z to the power r minus 1 minus 1 by z square z to the power r is going to. So you can take common as this term. Z raised to r minus 1 upon z is z raised to r minus 2. Z raised to r upon z square is z raised to r minus 2. So this is your variable, it is never going to equal to 0. So what is 0? You get r square minus r plus r minus 1 going to equal to 0. So similarly, you get r square minus 1 equal to 0 and value of r is 1 and minus 1. So two independent solutions for differential equation with respect to z are z to the power 1 and z to the power minus 1. These are the two solutions of d2y by dz square plus 1 upon z square 1 upon z dy by dz minus 1 upon z square y. So what is z actually? Upon z काय घेतला होता 3x minus 1. So these are the linearly independent solutions of one equation. This equation, but j equation I think टाका आपण after we substitution काय this equation. Solution is 3x minus 1 and 1 upon 3x minus 1. It is just like similar to this problem. Okay, let us have discussion regarding Wronskian and relation between linearly independence. Wronskian and linear independence. So as earlier we have defined transfer functions. Phi 1, phi 2, and phi n at x. What is Wronskian? Can anyone unmute and talk? So if you are writing n solutions, means definitely they are the solutions of n order differential equations. So first row will be the function as it is. Phi 1, phi 2. Mark your attendance. Phi 1 dash, phi 2 dash, and so on, phi n dash. And the last is n minus 1 derivative. This is Wronskian, it is function of x. It will be defined by this. आपण अगोदर वापरला theorem is similarly आहे where the if phi 1 phi 2 phi n Argand solutions of Lopez with variable coefficient on an interval Whatever order, that many solutions will be there. L of y in differential equation, differential order must have in order. That means that higher order, whatever order n, that its degree is 1. They are linearly independent. They are linearly independent. Do you remember the condition? What is the relation between Wronskian and independent functions? Whether it is with variable coefficients or constant coefficients, the condition remains same. Whether I should write it is equal to 0 or not equal to 0, and talk to me. What should I write here? Yes, Chaitanya Rose.
Yes, sir.
What should I write here?
Is not equal to 0 Wronskian of
Okay, very
phi
good.
1 phi 2.
Wronskian should be not equal to 0. जसं आपण थेरमचा प्रूफ केलं ते विथ कॉन्स्टंट कोएफिशियंट. ते कोएफिशियंटचा काही संबंध नाही, आपण त्याचप्रमाणेच प्रूफ करणार आहोत. फक्त ऑर्डर जेवढी आहे तेवढेच त्याचं सोल्युशन असतील इंडिपेंडेंट, ही गोष्ट मात्र तुम्ही कायमस्वरूपी लक्षात ठेवा. Whether it has constant coefficients or so if I only proof आहे, तर प्रूफ कळलं नसेल तर रिपीट होईल या ठिकाणी. फर्स्ट सपोज Wronskian phi 1, phi 2 and phi n at x not equal to 0 for every x in I. So converse part we are assuming. We want to show that phi 1, phi 2, phi n are linearly independent. Phi 1, phi 2, phi n are linearly independent. That is, if there are scalars one actual definition of linear independent, if there are scalars such that C1 phi 1 plus C2 phi 2 and so on, Cn phi n equal to 0, what should you have? What should you have? For all x in I, you must have C1, C2, Cn all 0. You must have C1, C2 all 0. आपल्याला दाखवायचं C1, C2 सगळे 0 येतील, त्याच वेळेस ते काय असतील इंडिपेंडेंट असतील. आता आपण याचं काय करायचं, फक्त n-1 टाइम डिफरन्शिएट करायचं याला. त्याच्यावर मी पुढचे इक्वेशन लिहितो. C1 phi 1 dash plus C2 phi 2 dash, just differentiating, and these Ci's are constants. Phi n dash, this is going to be second time differentiating. To get n equations, you must differentiate in n-1 times. So I'm continuing this. C1 phi 1 n-1 derivative, C2 phi 2 n-1 derivative, Cn phi n-1 derivative. So this is a system of homogeneous equations with unknown C1, C2. So I can write this in matrix form. Phi 1, phi 2, phi n, phi 1 dash, phi 2 dash, phi n dash, and so on. Phi 1 Cn minus 1 derivative, phi 2 Cn minus 1 derivative, and phi n's, and our variables are C1, C2, Cn. Okay, continue. Dangerous. Star is real system of homogeneous n unknowns. कोएफिशिएंट, आता हा कोएफिशिएंट आपण पाहिला, पण a x equal to 0 असेल. Determinant of A is nothing but your Wronskian phi 1, phi 2, phi n x, which is never going to 0. If determinant is non-zero, that implies rank of this matrix is n, and which is equal to your number of variables. What it implies, it has trivial solutions. In that case, if you study that linear system of equations, it has trivial solution. So trivial solution means your C1, C2, Cn is your x matrix. This is going to be equal to C1 is 0, C2 is 0, and so on. Cn is 0, which implies phi 1, phi 2, phi n are linearly independent. What the solutions of L of y equal to 0. This one part similar to that previous that we have discussed. Now that was the converse part. If your Wronskian is, if your functions phi 1, phi 2, phi n are linearly independent, we're going to show that Wronskian is non-zero for all n. Suppose phi 1, phi 2, phi n. Who are the solutions? Which are solutions of L of y equal to 0 are linearly independent. Are linearly independent. What is claimed? Wronskian of these independent. एक एक असताना त्या ठिकाणी त्याला तो 0 होईल. आपण कॉन्ट्रडिक्शन साठी करूयात. Suppose there exists x naught in I such that the Wronskian of phi 1, phi 2, phi n at x naught becomes 0. आपल्याला कोणताच पॉईंट मिळत नाही असं दाखवायचं का? कोणत्याच पॉईंटला Wronskian 0 होत नाही. आपण असं म्हणूयात की एखादा पॉईंट त्या ठिकाणी आहे की त्याच्या ठिकाणी Wronskian काय होतो? 0 होतो. Wronskian 0 होतो म्हणजे काय? आपण जर मगाशीच इक्वेशन मध्ये किती ठेवलं C1 phi 1 at x naught plus C2 phi 1 phi 2 at x naught plus and so on Cn phi n at x naught. नंतर C1 phi 1 dash Wronskian at x naught आणि आपण त्या कोएफिशिएंट मल्टिप्लाय करतो. Plus C2 phi 2 dash at x naught so on Cn phi n dash at x naught. Last statement C1 phi 1 n minus 1 at x naught plus C1 phi 2 n minus 1 at x naught. Okay. These equations can be written from Wronskian. Or you have this system of equations at point x naught. I can call this a double star. Of equations at naught. त्याचं केअरफुल ऑब्झर्व केलं आपण इथं. हा ax इक्वल टू 0 असा लिहिला. हा a म्हणजे डिटर्मिनंट, a म्हणजे कोण आहे? Wronskian at x naught आहे, जो 0 आहे. हे याचा कोएफिशिएंट मॅट्रिक्स डिटर्मिनंट काय आला? 0 आला. Wronskian तो त्या पॉइंटला 0 म्हणजे 0 आला. म्हणजे आपल्याला त्याची रँक काय येईल? Rank matrix order less than n, which is not equal to number of variables. When rank is less than number of variables in the system of English equations, then there exist C1, C2, Cn, not all 0, such that Ax equal to 0. At that x naught you are going to write. What do you mean? C1 phi 1 phi 1 at x naught, C2 phi 2 at x naught, plus Cn phi n at x naught equal to 0. with not all C1, C2, Cn are 0. So ये linear combination ऐसा है C1, C2, Cn ही 0 रहते हैं equal to 0 देखने पे डेफिनेटली एक फंक्शन psi ऐसा है तो यांचा linear combination आपण लिहू शकतो phi1 plus C2 phi2 plus Cn phi n आणि याच्यात आपण इझिली चेक करू शकतो L of psi equal to 0 because these are scalars L of phi1 L of phi2 and L of phi n all are 0 so L of psi can be verified. This can be verified. And what is psi at x naught, psi dash at x naught, and so on, psi n minus 1 at x naught. From above double star equations, the psi at x naught म्हणजे काय C1 phi 1 x naught, C2 phi 2 x naught, Cn phi n x naught जो 0 आहे आपण वरती दिले double star कडे पाहिजे. This is your psi at x naught, psi dash at x naught, and so on. So everybody is going to 0. Everybody is going to 0 there. So by uniqueness, आपण uniqueness theorem पाहिलं होतं काल. By uniqueness theorem, your psi of x must be 0 for all x. Psi of x 0 म्हणजे काय? C1 phi 1 plus C2 phi 2 and so on Cn phi n is 0. There exist C1, C2, Cn not all 0 with linear combination 0 implies phi 1 phi 2 phi n linearly. Actually what is given they are independent. So this is the contradiction. So what we assume? We assume that there exists one point at which Wronskian is 0. It is totally wrong. We assume that there exists one point at which Wronskian becomes 0. It is wrong. So this is not possible. Not possible means Wronskian is completely non-zero. Phi 1, phi 2, phi n at x compulsory non-zero. So these are the necessary sufficient conditions to get your functions to be linearly independent. Similar, it is similar theorem to earlier. Okay, I'm going to write statement of next theorem.
सर
बोला.
रेकॉर्डिंग सेंड करा ना.
हो हो करणार आहे. This result is also similar to that. I'll just make a statement of this theorem. Let phi 1 to phi n be n linearly independent solutions of L of phi equal to 0 on the interval into I. And if phi is any solution, if phi is any solution of L of phi equal to 0, then this phi can only be written as linear combination of this. And this has been discussed similarly in the case of constant coefficients. So you can do in the case of variable coefficients. There is no change in the proof. Where this C1, C2, Cn must be constants. Vice versa, any set of n linearly independent solutions are still, it will form the basis for solutions. Every solution is linear combination of this. That means every solution of this L of y is linear combination of this. Whatever solution space, the n dimensional vector space you consider here, phi 1, phi 2, phi n will be the basis for that solution space of L of y equal to 0. Next, this Wronskian formula is also discussed in the previous unit. Can be discussed similarly here also. The formula for Wronskian. How Wronskian can be computed. If phi 1, phi 2, phi n, the n solutions of L of y equal to 0. Not mention they are linearly independent. Just mention that, okay, they are the solutions of L of y equal to 0 on an interval I, and x not be any point in I. So one need to calculate the Wronskian of phi 1, phi 2 phi n at x. It is just exponential of minus integration x naught to x. The second coefficient, that is yn minus 1 coefficient a1 t dt, and it is multiplied by the Wronskian at that point x naught. हे सुद्धा आपण डिस्कस केलंय. सिमिलरली राहील ते सेकंड केसला आपण डिस्कस केलंय, त्याला जनरलाइज केलंय प्रमाणे. सो the proof we can refer for there. And the important corollary on this, we'll have this corollary stop. Next time we will have example on that. If the coefficients okay, of L are constants, okay, it is mentioned here are constants, then the Wronskian of phi 1, phi 2, phi n at x. This is similar corollary to earlier one. Exponential of minus a1, who is a1? A1 is a coefficient of n minus 1 derivative. X minus x naught into Wronskian of phi 1, phi 2, phi n at x naught. हे कॉन्स्टंट कोएफिशिएंट्स आपण अर्लियर युनिट मध्ये डिस्कस केलं होतं. स्टेटमेंट मेन्शन केलं आहे ठिकाणी. Okay, in the tomorrow's lectures, we have some exercises on this. Later on, we have to discuss the reduction method. Whatever we have done in for with linear equation with constant coefficient, similarly, we'll do it for with variable coefficient. Reduction method. This unit will be mostly similarly likely to your unit. So we have to focus on more example instead of theory of